Hey, hello everybody, welcome back. So last video actually discussed some results of comparing square wave and sine wave, at least using a MATLAB frequency response Fourier transform to kind of just see what the responses are like, okay, in decibels. Alright, so we have some data here, and that was the square wave and sine wave. I described some similarities and differences, and if you plot in decibels, it's a lot harder to see the subtle differences between a square and a sine wave in the Fourier transform, the frequency domain. So you can see that what I'm trying to bring across is that they're very similar. If you cannot use sine waves to test your machine or whatever, you can use square waves. Okay, so now let's talk about something else. I was saying last time that you probably want to test more than one frequency at one go. So because frequency response testing, especially for low frequencies like 0.01 Hertz, can take maybe 20 minutes. You go 1 times 10 to the minus 3 Hertz, with a very low frequency. It might take several hours just to run a test. That's not quite ideal, right? So we wanted to put many signals together, and let's show what they are like. Okay, last time I was trying to do a sum of frequencies, okay, and meaning to say I will have many sine waves added together. Okay, so what I'll do is this: I have a fundamental frequency, then I have a fundamental frequency times 2. Okay, then I'll add both of these signals together, and I will just have a up and down kind of a thing. Okay, so originally I was just thinking about thinking about this using this signal. Let me close this probe. Yeah, I will have two of these signal generators. And I'll just sum up the contribution of both of them. But let's see what happens. Okay, let's see what happens when we do that. Okay, so let's see. So what I do, okay, originally is to have two signal generators. Okay, I'm not going to put specific inputs to them. Okay, but I'll just say that, okay, this is a sine wave of amplitude 1, offset 0, and frequency 0.5. Okay, if I add two identical waves together, what will I get? Okay, so I will just add both of these, and I will put them into a graphing VI, sorry, sim time waveform. Okay, so this I will put here, and let's just press play, and we'll see what happens. Okay, so you can see that when you sum two sine waves together, okay, when you sum two sine waves together, you will have a bigger sine wave. Okay, the amplitude will be not 1 anymore. If you want the wave amplitude to be just 1 unit, it will not be 1 anymore. It will be 1 plus 1. The amplitude will become 2. Okay, and that will happen regardless of the frequency which you set it. So if I were to set this at 0.1 Hertz and the other at 0.5, okay, we will have also the waves will not cancel each other out. So you can see that you will have this sort of a sine wave shape. Okay, and it will vary between -2 and 2. Okay, so this is a summation of two frequencies, which was, when we first started out our broadband, which means you want to have more than one frequency. You have a band of frequency instead. You will have this situation happening where if you add two sine waves of amplitude 1, it will become like a sine wave of amplitude 2. Okay, so you don't really want that to happen. Okay, so we'll need to think of a way such that when you add both of these sine waves together, you will get a sine wave of amplitude 1. Then you kind of scale it as and how you like it. So how do we do that? Okay, So that's this problem. I kind of sorted it out in this sum of frequencies Vi. So how do we solve it? Okay, I give I have a fundamental frequency waveform generator. Okay, fundamental frequency times 2. So I put in the frequency in here through the node, and I also give the frequency into another node, which is over here, and I'll just use I'll multiply that by 2. I'll have a fundamental frequency times 2. Okay, then whatever frequency that I'll multiply by 2 again to get fundamental frequency times 4, fundamental frequency times 8, fundamental frequency times 16. So all of these are sine waves, all right, of various frequencies, but all of them have the amplitude of 1. So I will just add them all together using this node here. I assume you know already, so this is not introductory LabView anymore. So yeah, but I added them all into this node, which you can find over here in your numeric compound arithmetic. Divide everything by 5, so that gives you a sine wave of amplitude 1. Okay, so this compounding all of this together will give you a sine wave of amplitude 1. Alright, okay, so that's all well and good. So once you divide by 5, your oscillations will be of amplitude 1. Then you can multiply this by whatever amplitude you set your Vi to be, and this is just adding 5 frequencies. All right, you can add more if you want, but you know, it's a little bit problematic if you want to keep adding maybe like 30 frequencies. You know, that's going to be a bit harder. Okay, so so basically I do all my adjusting, you know, to set the amplitude and the offset at the end of the thing, because you know that's where things add up, and then the output will be not numeric. I guess it's a sum of frequency signals. Okay, so this is what they should be. Okay, so I add some notes here. This is where I do the adjustment of the amplitude and the offset, because you know, the waves add up. So you do not set the amplitude and the offset here. You set it after you add everything up, and you normalize the amplitudes. Okay, and of course the signal type is determined for every single sine wave. Okay, or maybe not sine wave. Okay, so this is how my Vi actually works on the simulation subsystem. So this is the first one. It will give you maybe 5-ish frequencies to work with. Of course, you can actually use more of these VIs, and then you can get multiples of 5 frequencies at one go, so you have a lot of frequencies. Okay, so let's try this thing. Okay, so I'm going to play this. This is where the waveform chart is going to be for this sum of frequencies. So I'm adding about 5 sine waves here. Let's put the offset at 15 and amplitude maybe a 2. Okay, so what I want you to focus on is the blue colored plot, which is in the middle, the very up and down looking plot. The signal type is sine, and you can see it's a very, very jagged signal. Very jagged signal. So if you want a square wave, this is what you will have. Now, unfortunately, if you were to do this square wave thing, you'll see that the values actually vary between 13 and 16, or 16 point something, not 13 and 17. So that's not exactly what you want, because this oscillation is kind of uneven. Okay, this oscillation is uneven. With a sine wave, it does the what do you call that? The amplitude does not even reach 17 and 13. Okay, you're supposed to have a sine wave that goes up and down between 17 and 13. But you know, some of the sine waves actually cancel each other out. That's why you never get there. You just have a very, very jagged kind of a graph. But okay, so that's one way. You can actually just run a Fourier transform on it, and yeah, we'll see what happens. Okay. So now, I hope you believe me. If I were to say, I already have this sum of frequencies. Okay, this sum of frequencies, LabView data, and we can analyze the waveform. This actually went up to 10,000 seconds. That's a lot of time. Okay, so let's do this. Sum of frequencies. No, I better open with. Yeah, better open with LibreOffice. I'll save it as a CSV. Sum of frequencies.csv, and not only that, I'm just going to put this as my. Yeah, I think this is a sum of frequency, the sine wave, because this actually oscillates between 16 and 14. Okay, let's see what. Tell you what, we'll just do a few. Yeah, we'll do a few of this. Okay, I'm gonna insert a chart. Okay, so this does look like a sine wave looking thing. Yeah, it's a sine wave looking thing. So it's safe to assume that this is actually a sum of sine waves. Okay, it's a sum of sine waves. Okay. Yeah. So that's done actually. I think taking the fundamental frequency to be a bit lower. So let me close this one. Yeah, let's make the frequency a bit lower, maybe 0.01. Maybe we'll be able to see the differences. Yeah, okay. So this is much better when you have like more resolution. I mean that my time step for this solver is 0.1 seconds. So if your frequency is so high, you will not be able to see very much of that sine wave looking pattern. Okay. And now the square waves are also, I mean, yeah, okay. The red lines I'll talk about later. But you can see this is a very sine wave looking thing. And the fundamental frequency is 0.01 hertz. It never quite goes down to like the signal doesn't go down to like 13 or what. It goes near that value but not at that value. Again, because probably the waves actually cancel each other out for some reason. Yeah, it's just superposition, you know. But yeah, what we can do is just analyze this signal in MATLAB. Okay, we can analyze this signal in MATLAB to see what happens. So let's see the CSV file. Okay, I'm just going to copy and paste the exact same frequency here, exact same signal, in here and here, because that's how I kind of coded my MATLAB to do it. So, oh shucks, let me cancel. Save as CSV, sum of frequencies.csv. I'll put this here. So let's take the sum of frequencies.csv and we'll just pump it through MATLAB. Okay, and we'll take a look at the signals. This should actually, of course, get us into a very clean, clean signal. Okay, sum of frequencies.csv. Okay, so let's put this in here, sum of frequencies.csv. Okay, so you can see the average value of the input output is pretty much the same. They're actually the same signal, of course. Oh, bother, I gotta clear that. Okay, so I'm going to run my script and let's take a look at our sum of frequencies. Okay, so you can see the sum of frequencies here. I have 5 frequencies. This is 1 times 10 to the minus 3 hertz, not 1 times 10 to the minus 2. So it's 1 times 10 to the minus 3 hertz, 2 times 10 to the minus 3 hertz, 4 times 10 to the minus 3 hertz, 8 times 10 to the minus 3 hertz, 16 times 10 to the minus 3 hertz. So this is where all our peaks are. Okay, and you can see, yeah, most of the peaks are over here where we want. The rest is more or less noise, and you can see all the amplitudes are more or less the same. Though, if you look closely, the amplitudes actually so-called decay with time, decay with increasing frequency. Okay, but they don't decay that much. This is a very, very clean signal. So I want you to keep this in mind when I guess we move on to the next thing. Okay. So the next thing I want you to observe perhaps is the square wave. Okay, we can actually change this to a square wave. Okay, because I have programmed my amplitude, offset, and frequency here, and I made the sub VI. For some of frequencies, you can change it to a square wave if you want. Okay. What will you notice? Yeah, it will be a square wave looking thing. There's a lot of steps up and down. Okay. Okay, so what you'll notice is that again, it may not be the most symmetric, because the square wave sort of spends more time below 15 than above 15. If you notice what I mean here. Yep. Okay, maybe I was wrong. Okay, it's going. Okay, but as of now, I can't really tell we just by looking, what the oscillations are. But this is a square wave input, and you got to set the frequency low enough so that as the solver actually solves the time step, you're able to see what's going on. Okay, so this is a sum of square waves input. Okay, and this is again good if you cannot have a smooth sine wave oscillating up and down, so it's better to use square wave. Okay, but even better, I mean, square waves are useful if you can only adjust your controller to discrete values. But if you can have only two values, you can adjust your controller to, then you need something a little bit more extreme. We call them binary signals or binary approximations. Okay, so what's a binary approximation? Well, I guess I'll have to talk about that in the next video, because I'm running out of time. I don't want my videos to drag very long. So, okay, just in summary, what have we covered this video? We covered some of the principles behind planning a summation of frequencies VI. What's the algorithm like? And yeah, you see the proper way to do it, such that you have your desired results. And next video we'll probably talk about binary signals. And of course here we have square waves as well. We can of course do a Fourier transform on this kind of a graph and not be a problem. I think I'll just leave that out for the next video. Okay, so thanks for watching.